Hello world, welcome to Building a Roguelike in C, the stream where we are building a classic ASCII roguelike using no pre-built engines of any sort. We're building it all from scratch, including building out the various algorithms necessary for displaying graphics and determining procedural content generation, all of that good stuff. Which brings me to where we left off last stream. Let's just jump in real quick and see where we left off. We were working on field of view, and so we had implemented a very simplistic field of view algorithm where basically we're casting light out in the four primary directions, so we have like a square of light that follows us around the dungeon. We got that working. So there's a couple things that I'd like to try and tackle today. I think the first of those will be to build in the concept of places where we've been and remembering the places where our hero has been. So let's jump into the code, and I think I don't think that this code necessarily will fall under the field of view code. It's more of the stuff we've seen. So it's world state indicating places we've been. Let me refresh my memory as to how we did our render screen. So what we're doing right now is we are looping through all of our visibility components in our world state. We're grabbing the position of those components, and if we have a position that is visible, we are drawing it to the screen. After we test if it's in our field of view. So we incorporate our field of view map here as well. So I think we may want to incorporate our history into our visibility. That seems to make some sense. So we'll add a bool here. Has been seen, I guess. And so what would be the best place to put the update for that property? So we could certainly incorporate it into our render loop. That doesn't seem like the best place for it, though. Maybe that should be part of our FOV calcs. I don't like that either, because then we're conflating our FOV calculations with our world state, which I don't necessarily want to do. We've managed to keep them separate. FOV right now is concerned with generating and keeping current this FOV map, and so I don't want to then start throwing in knowledge of world state as a dependency. So I guess this is the place to put it. For every time we see a new I guess we can make it conditional. Let's see. How intensive is updating our world state? So what we're going to do is we have a reference to our visibility component. I guess we would be updating and then adding the new component? Or do we have... I believe we've got a reference to it. We can just update it directly. So it would be visibility comps at our position I, and then we mark the has been seen to true because it's been seen now. But what we also want to do is if we fail this condition, we want to check and see. So failing this condition means that it's not currently in our player's field of view, but what we want to check now is if it has ever been seen. And so what we'll do with cells that have been seen but are not currently visible is we will render them slightly differently. We'll render them in a different color, I guess. Faded color, perhaps. So if it has been seen, then we still want to do a put char. But we don't want to have it be the same colors. So for now we could just have it be like a predefined gray color of some sort, or we could... It would be kind of cool if we just... if we play with the alpha. Well, just to test our stuff, let's set it to like some obvious color. We're not going to mess with the background. Well, maybe we will. Maybe we will mess with the background color as well. But for now, we'll just do. We can make it be all red. So have a full on red, and then green and blue is off, and then have it be full alpha. And leave background color alone for the time being. So let's walk through this. If it's in our field of vision, we mark it as seen, and we put the character glyph on the screen according to the foreground and background color settings. Otherwise, it's not currently in our field of view, but we check if it has been seen, and if so, then we render it with this red color for now. So So let's test the effects of those changes. Okay, let's run it. All right, so now as we move, those walls have become there as they fall out of our field of view. They are still being retained and drawn to the screen as places that we've been. So that seems to be working. And then when we come back in, they're rendered back as the brown that we're used to as being as part of our current field of view. All right, so that works. I'm happy with that. One thing that, I mean, obviously the red is kind of a hideous color. So what do we actually want to, it served the purpose of testing, but what do we actually want to render our historical cells at? We can render them all in like kind of a uniform gray, but I think what I would prefer to do is render them on a, I guess, a black background for now. Let's just do straight black background, but what I want to do is render them as their foreground color, but tweak the alpha value so that they're dimmed out. So let me show you the in my console library, I have this copy blend, colorize pixel. What is colorize pixel? I need to, I don't even remember what my own functions do anymore. Let's just look real quick. Colorize the destination pixel using the source color. I don't think that's what I want. Where am I using that? I believe that's in my blend. So what I want is I actually want to change the color. I don't want to. So I may want to make use of these this color from RGBA. So what I'm going to do, and we can do this. Well, we have to do it at this level, because it could change. So what we'll do is we will have a, we'll say faded color, and we will set that equal to so the color that we want is here, visibility, foreground color. Let's just collapse this for the time being. And then, so the format of our pixels in terms of color scheme is RGBA, so it's a byte for each of those components: red, green, blue, alpha. You can see that up here. So what we can do is we can just set the lowermost byte and thereby set the alpha component. So, but if we OR it, that's not going to work.
Turn on.
So we could do something like this. Set our full color to this. And then set our faded color to and then within each of those we do our red component for full color, our green, blue, and then we set alpha, and we would set alpha to be what do we want it to be? Full on alpha, which means full opaqueness, is 255 or FF. So we can set it to, let's try it right now on like 5.5 or something. And we need to fill in our full color. Grab the components from that. And then instead of setting it to our garish red, we set it to our faded color. So let's give that a try. Alright. And it is working, but I think perhaps that might be a bit too faded out. Like I can see it, but it's very dark. I like the effect though, so I think we just need to tweak the number. Make it a little bit brighter. I mean, I'm not talking major brighter. Maybe instead of the 5.5, let's make it 7.7. We can try that. Okay, I like that. I think that works. Cool. This map I'm not thrilled with. Look at all this Swiss cheese. I have that on my to-do list. We will be fixing that up in the next couple streams for sure, because the maps work. They're randomly generated, and they meet our criteria of having all the rooms accessible, but they are ugly right now. They are not looking good, because all of these corridors are crisscrossing and chopping rooms into pieces, which is not, it just doesn't look cool. Hey, Mr. Fourth Dimension, how's it going? I would love to be using 4Coder right now, but I am having some issues getting it to show up as a for window capture in OBS. It does not. It doesn't like it. And I remember you said something about the buffering or putting it in a special mode, but I need to play with that a bit more because I'd like to be able to use the excellent forecoder for my code streams. Okay, let's. So what else do I have on my to-do list? Yeah, I'm a big fan of classic roguelikes, and I'm kind of as I've said before, dusting off the C parts of my brain because it's been a long time, and I haven't done any really large-scale programs in C before. But it's refreshing to kind of get back down to the lower levels and really diving into algorithms and data structures that I haven't played with in years. Yeah, definitely. If you could help me troubleshoot it, I would appreciate it. All right, So we're showing now our history of where our player has been. So there's a couple things that we could work on. I think I would like to finish up the field of view work and do it more. Do a more complete implementation where we're not just being followed around by this square of light. So there's an algorithm known as shadow casting that basically you shoot out beams of light and figure out what's visible and what blocks other things behind them. And what casts shadows, so it essentially hides things behind them. And I've been reading up online. There's a lot of blog posts, and there's stuff on Rogue Basin that kind of describes the algorithms in various programming languages. I'm trying to. I don't want to just copy an existing implementation because part of this exercise is to dive into the algorithms myself. So I've got my handy-dandy notebook out, and I've been spending the last couple of days trying to suss this out. So I've written down some pseudocode here for myself, and I actually drew up a diagram of how I think it works. So let me. Of course, I was unprepared and didn't pull that up. Let me pull that up real quick. Let me see. So I am pulling up a program called RexPaint, which is an excellent application for doing ASCII art, which is perfect for classic roguelikes. Hold on, I need to load this up first. And of course, I can't see it. Let me load it up real quick, and then I can present it. All right, there we go. So basically, shadow casting. The algorithm that I'm going to use right now will basically be, pick a highlight color here. So I drew a simple diagram here of a sector. First things first, this is my player right here. And so what I'm going to do is I'm going to determine the field of view 360 degrees, but it simplifies things to treat it as 8 different sectors. So if you consider the north, south, east, west lines flowing through here, and then the 2 diagonals to chop it into 8 sectors. And then think about a single sector and solve the algorithm for that, and then the rest of that algorithm can basically be applied to all 7 other sectors just by doing some transforms on the XY. So let me consult my notes here. So the basic plan is to scan from your hero to some distance in the, some value in the distance. And I think for my purposes, I'm probably going to make it be like 5 or 6 based on my current map size. But what the algorithm is basically you scan across each subsequent, this is called, I think, a span. I've seen it called. So you gradually grow farther and farther away from your hero, and if there's no blocking items in a given cell, then we're okay. You can see that cell, go ahead and render it. It starts to get interesting when you hit a cell that can block, and so that's a better cursor. So there we go. Okay, so when we hit this guy here, this is going to be a wall, and so what that's going to do is it will essentially, we'll have some calculations to generate the slope of the line between here and here. And so when we mark this down on our map as having blocked, we add and calculate the shadow slopes, and we calculate it from the left edge of this as one of our slopes, and then the right edge of the other, the right edge of this as the ending shadow slope, so that essentially it starts casting a shadow, and of course, like, this is an approximation, but what it does is, as that, if you extended the slopes of those lines outward, you would see that all of the stuff behind it here is obscured. And so it doesn't even need to be checked, because the algorithm on subsequent lines is we check and see if the given cell point, we calculate the slope here, and if that slope falls between the starting and ending slope of a known shadow, we just throw it out, we're done, you can't see it. And so essentially, as we move further and further away from the hero, we collect known shadows, and we apply those known shadows to our subsequent cell checks. So I don't think I described that very well, but hopefully it'll become clear when we start putting it together. So close that up and consult my notes, because I have several pages of notes. And this is definitely going to fall within our FOV calculations, so we'll work here. Alright. So resetting FOV to default state, that's still relevant. And then our last step, applying visibility to the FOV map, is also still relevant. So for now, we'll just comment out the simplistic algorithm. And we're gonna need some variables. So first we're gonna need I guess our span, calculate that. We need something to indicate our previous blocking. So essentially the algorithm is, so for we'll start with 1 because distance 0 would be at the location of our hero, so we don't need to check that. We know it's visible. So while d is less than our we do have FOV distance already declared. And I think, okay, so this is and so for each, basically for each distance from 1 to our FOV distance, then we're going to want for each cell, so for each cell from 0 to our span width. So what we need to do is declare our span, which I think is going to be equal to the distance. Let's see. Oh, a span is our current distance plus 1. That's what it is. So int. This will be our x. Well, x is less than d plus 1, I believe, less than or equal to d plus 1. And then the first calculation, we need to determine if the cell that we're about to examine is even in our view distance, because as we get out towards the, if you had like a full square, as we get out towards the diagonal edges of our square, some of those are going to fall outside of our range, because we want our range to be a radius, so a circle with a radius of our FOV distance. We don't want the square following us. So the first step, I guess the first step is to figure out what cell we're working with. So we're going to need I'm just going to call this FOB cell. So we're going to have an FOB. How about some naming conventions? Let's follow our own naming conventions. Sweet. FOB cell. What we're going to need to do is we're going to need to, again, I said we're going to divide the space around us into 8 sectors, so we need to map that cell's coordinates in, we have to essentially normalize them so that we know what we're dealing with. But I guess we can calculate view distance without actually normalizing first. How about if we write some pseudocode? That would be brilliant. So this is going to be for each distance. To FOB range, and then within that we'll do for each cell in span, and then once we're within a span we want to say is the cell within our view distance? And then, if so, we would like to say, is that cell within a known shadow? Okay, and if it is, then we're done, right? If it's not within the known shadow, then we mark it as visible. Okay, so we mark it as visible as our first step, and then what we want to do is we want to check and see if it's blocking. So blocking. Because we know it's not within a shadow, but now we need to check if it's blocking to see if it's going to create its own shadow. So if that cell is blocking, we need to check if let's do this so that we're not getting so we check and see if the last cell was blocking too, because we want to accumulate shadows. If we have several in a row, we don't need to recalculate we don't want to recalculate the starting slope, because the starting slope would be to the left of us if we're talking about sector 1. So we want to see if the last cell was blocking, and if so, then we want to accumulate our shadow. But if it wasn't, then we need to calculate the start of a new shadow, right? Cell blocking. Okay, and so now we we'll add that to a shadow list, but so here we're at no, our cell wasn't blocking. So our current cell is not blocking, but we still need to check if the last cell was blocking. Because if it was, we need to calculate the end slope of the previous shadow. So we calculate the end of the shadow slope, and then we add it to our shadow list. And we want to add to our shadow list. And I think that is the algorithm for our one sector of our FO view. So what we want to do essentially is this big for loop 8 different times, and we're going to be transforming the cells so that we can treat them as a triangle that looks like that. Alright, so we're going to need some functions here. We're going to need several functions. So the first function that we're going to need is we're going to need to calculate the distance between 2 points. And this is going to be I guess we return a float from this. And we'll send in 4 points. So we'll send in our x1, y1, and our x2. Yep. And so we can use our excellent Pythagorean theorem to calculate our distance, because essentially we draw a right triangle and then we calculate the distance between as our hypotenuse, the length of the hypotenuse. So essentially what we want to do is calculate our distances between x, and these will all be transformed, so I think that we can assume that they're positive numbers. So we can do We have our float. I need to look up my... I don't even know the standard math library functions. I need to look up those names. So we've got square root, and then, oh, power. Okay. Everything works in floating point numbers, though. So I want to raise that to the power of 2. And then we want to add to that our y's raised to the power of 2 squared. And then what we want to do is take the square root of that whole thing. So I guess we can just return that whole. So what we want to do is to test if our cell is within the view distance. So in this case, the cell that we're examining is going to be so we want to see if the distance between those points is less than or equal to our FOV distance. So what we need to do first, move the declaration of this up so our function can see it. Let's just get rid of this. We're not going to want this anymore. So what are we comparing? We are comparing our initial x and y. Oh, I see I've got a naming conflict here. So what do we, oh, we want to call this, let's call this cell x. So this will be our cell x. So what we want to calculate our distance between is our hero, which is at xy, and then we want to calculate our cell x and cell y. So we've cell x is our the value across this inner loop, and then our y, our cell y, is going to be this distance d. So maybe we should just call it cell y. Seems to make more sense. So if the distance from our hero to the cell that we're testing is within our FOV distance, then we'll continue. Otherwise, we're just not even going to look at it. So next we want to know if the cell is within a known shadow. And so now we're going to need to take a step back and figure out how we're going to keep track of our known shadows. But we can write the code that calls our, or that uses those bits of data, so that that will hopefully inform us as to how we want to shape that data. So we'll do let's say cell in shadow. Cell is shadowed, maybe? I don't know. Cell in shadow. So again, we're going to want to send in the cell that we're testing. So that would be our cell X and Y. And known shadows. Send a shadow list. Okay, so in this case, if we know that the cell's in shadow, it means it's not visible, which means we can be done with this loop. So really the yes becomes we bail on yes. We don't need to. So what we want is while our cell is not in the shadow, or if our cell is not in the shadow. And what we'll do is we'll mark it as visible.
It seems impossible, but there's nobody else I want by my side to stand in with me to take this fight through the rise and fall.
Okay, and then we need to check if it's blocking. So we're going to need to grab our world state, access our world state to determine that. And we do that. Do we have a lookup for based on? What we're going to need to do is get the loop through our visible objects and see if it's a match. Seems non-optimal. Let's hide that behind a function for now so we can keep working. Seems like we don't need this cell structure that we defined. Alright, so if yes, otherwise, so if our cell is blocking, we need to see. We need to check and see if the last cell is blocking. So we had, if you remember, we declared a variable for that. And then here again, we want to check. What's the last cell blocking? And as it matters. Oh, these both goes. Sorry. Whoops. So that's right. We don't have an else for. So I think last cell blocking, we want to accumulate the shadow, which also means this cell is blocking and the previous one was blocking. Accumulating the shadow isn't okay, I'm just thinking about some cases here. So we're going to need some variables that are outside the loop because we're going to need to hold those values while we're in the loop. So we'll have a shadow start. I was just thinking that there's a possibility that we don't end our shadow properly. So in that case is if the shadow begins in our span and then the blocking components end outside of our span, we would never end that shadow and add it to the list, and we need to do that. So when we hit the end of the span, and before we go to the next span, we need to see do we have an open shadow, basically. And if so, If so, add it to the list. So in this conditional check, kind of occurs to me that the yes case here doesn't matter, because if our last cell was blocking and the current cell is blocking, we don't have any work to do yet. We only have work to do if it's the start of a shadow or the end of the shadow, and in this case we don't know that we're at the end of the shadow yet. So what we want to do here is just say if collapse this, create a new shadow. So, Yep. And just like in our else case, we only care if the previous cell was blocking. If this cell is not blocking and our previous cell wasn't blocking, we don't have any work to do, so it's not. Alright, so creating a new shadow is essentially we're not really creating a new shadow, we're calculating the start of a new shadow. And so what we're going to do is we're going to set our shadow start equal to or let's see, we've got FOV distance between, we can do line slope. And again have our X, Y, cell X, and cell Y.
That's how we do it.
Okay. It's the last cell blocking. Now we have a bit more work to do. So we do calculate our shadow end. Here's the same. There's a problem here. And the problem is that we don't want to calculate the slope of the line. What we want to calculate is the slope of the line from the very left edge of that cell. So if you can imagine like the grid of cells, each cell being one by one, and we're considering the cell coordinate as being the center point of that square, the leftmost edge would be half a point over. I'm wondering if that's worth to worry about. Maybe I'll leave a note. And then this similarly would be the right edge. Let's hey, and Dota Carry, thanks for the hosting. Appreciate it. Welcome. So our cell X, let's just do that for now. Did we mark our line slope? Okay, so that's gonna have to be a float. And this similarly will be okay, and then we're gonna have to, so alright, so we've calculated our shadow end. And then what we're gonna wanna do is add the shadow, the start and ending slopes, call that a new shadow and add it to our known shadows list. So I think what we need to do is add, instead of a let's do we'll do U32 no, yeah, shadows will have floats, so to be start slope and end slope. So we'll calculate a new shadow. Why don't I actually call it a shadow? Shadow. We will call it shadow start and shadow end. We'll send those in, and then we'll we'll add the shadow to our list of known shadows. And then similarly here, we will have an open shadow. We can recognize that we have an open shadow if we have a shadow start that is greater than 0 is not true. I guess if prev blocking is true. So we know that we never closed our shadow, because that's the other thing we need to do. We need to set when we close the shadow. Where do we set? Do I have a note in here to... That would be one of the first things that we do here, is initialize previous blocking to false at the start of our span. So if it's true, at the end, I turned up my headphones here. So yeah, if we have an open shadow, we're gonna do calculate our shadow end. We basically do this. Right. And then we can move on to our next span. So I think we've fleshed out our basic algorithm in terms of the higher level, and the rest is filling in the details. There's one more. I'm going to leave it to do for this because map loop through all 8 quadrants, or 8 sectors. I want to solve it for one sector and make sure that I've got the algorithm right, and then we can transform it for the other sectors. Okay, so we've got some functions to write now. And some data structures to define. So we've defined what one shadow looks like, but what we need to do is we need to have a collection of known shadows. And so right now I'm going to, we don't have the concept of a list yet in our code base. I think next stream I'm going to tackle the coding of your basic linked list so that we can have more intelligent usage of dynamic memory. But for now, I'm going to use stack memory. So what we're going to want is essentially an array of shadows. Call it known shadows. And for now, if our span and our distance is 5, I don't think that we can have more than 5 known shadows because they'll accumulate for a given sector. But just for giggles, I'll allow for 10. I'm just gonna have that be an internal which means it has file scope, but since we're doing a Unity build, it's essentially a global at this point. Known shadows, and then what we're going to want to do is also have keep track of our shadow count. So we have our distance between. So I guess the next is if the cell is within a known shadow. Oh, and we're passing our shadow list, so maybe. That makes sense. Let's get rid of. I guess I also have to pass in a shadow count, huh? So I have enough information to figure this out. So we know it returns a bool. And it'll take an X and Y, and then it will take an array of shadows and our shadow count. And we don't want to pass in our array as we don't want to pass it in by value, because then we're going to be creating copies every single time we call this. It's inefficient. So I'm going to go back on what I just did, and I'm going to move these out to a wider scope. For now. And so that's what our cell and shadow looks like. So what we want to do to calculate if a cell is in shadow is, first of all, we want to determine the slope. We need to send in another set of coordinates. Cell Y. I still need to send in X and Y here, because we need those to calculate slope. We could. Let's do this. xy, and then cell x and cell y. So that's the slope of the line that goes from the center of our hero to the center of the cell that we're trying to test. And then we'll say we'll pass in the cell slope, so we don't have to. Okay, so essentially what we're testing is we're going to loop through our list of known shadows, and we're going to test to see if our cell slope is within any of those known shadows. While it's less than our shadow count, right? So our known default is we're going to test and see if our cell slope is within the shadow slope. So we'll grab it's I, it's easier. It indicates that we're using an index. So I can call my shadow S, and that'll be known shadows at I. And so what we want to do is say if start slope is less than or equal to cell slope, and the end slope is greater than or equal to cell slope. Oh, not end. It's end. Yes. End. And I've got this wrong, because the cell slope needs to be greater than, yeah, so if the start slope is less than or equal to the end slope, and the end slope is greater than or equal to the cell slope, then it should be in our shadow. We can return immediately. I don't need a default case because the default case, if I fall out of my loop, is that we didn't find a match, so I can return false at the bottom of the loop. So if the starting slope I think that's right. So simple, now you see. Strike the match to set you free. Yep. Yep. I just realized we didn't do our line slope calculation. This will return a float. And we are going to return, so this will take floats. X1. X1, Y1. X2. So from elementary geometry, the slope of a line is the delta x or delta y over delta x. So in our case, delta y is going to be y2 minus y1 divided by x2 minus x1. Ah! That is not the key press I wanted. Alright. So that, we did this. We need to figure out marking visible. And you remember marking visible is basically in our FOV map we mark it to a non-zero or greater than 0 value because 0 indicates that it's hidden. I don't think we need a function for that. I think in our previous we used, well, for now we'll just call it 1. It's fine. Let's just double check our rendering code. Greater than 0, yes. Okay. Alright, so the next one is cell. We have to determine if a cell is blocking. And this is the... So this is the tricky bit. Because we need to tap into the world state. Trying to figure out the best way to do that. Let's write our declaration. Get that stuff out of the way. Alright, so let's look at our world state again. We've got our entity component system. Obviously going to need position. This is kind of a new, I just updated Sublime Text. That's new. Now when you hover over it, it tells you where it's defined. Excuse me, that's pretty cool. So what we're going to need to do is we're going to need to... We want to get the game object at a given position. Which seems like it would be a very useful function to have in the future. So it seems very useful. So maybe we'll write a function for that. Okay. Game object. For now, we can write a incredibly inefficient yet working version of that function by just looping through our position components and finding, seeing if we have one at those coordinates. So. What do we got? What do we call it? Something max go. That's what it is. That's a lot of loops. This will become a lot more efficient once we change our world state to be represented by dynamically growing lists as opposed to arrays. So I'm not going to worry about it for the moment. It will be, I think I'm just going to expedite our refactor of our world state. So it'll be a lot more efficient in a lot of ways. This is one of them. So. So what we'll do is position I'll just loop this into one big if, and then it'll short circuit if any of these conditions is false, so it won't necessarily test them all. So if all these conditions are true, that means that we have a game object at that position. So we should return that object, or a reference to that object. So what we'll do, essentially this game object's eye. And if we fall out of the loop, we will return null. Means we didn't find anything at that position. So, step one in cell is blocking. So, if we don't have a null, we're going to get the... No. Wait a minute. Where do we have our blocking? Wait a minute. Where do we... We don't want our visibility, it's our physical site. That's what we want. So we want the physical component of that object. Now we'll pass in our game object, and I think it's comp physical. We'll verify all this stuff. And we'll want to cast that. So we've got, yes, comp physical, and then our game object get component takes a pointer, returns a pointer. Yep. Alright, almost done. So now we do our if. And if any of this stuff is false, then we return. So if this is null, meaning there's nothing there, or block site comes back as false, then we're going to return false. The cell is not blocking. And I would like to change this name so that it's more clear that it's blocking site, not blocking movement, for example. I think that's the only time we test that. Yep. And now type Amy has to put our functions in alphabetical order. How's everyone doing on this Sunday afternoon / evening, based on where you are in the world? Alright, cell block site. We did line slope between, so it looks like we need add shadow. Add shadow, and then maybe some way to clean up shadows. So add shadow, it takes our shadow S, we're passing it by value. So that's going to operate on our known shadows list. So I guess we'll just, our shadow count will give us the index of our next available slot. Right? So we will do known shadows. Shadow count equals S, right? And then we will shadow count. We'll increment it. And that's pretty much all there is to it. Except for the fact that we need to declare it before we use it, so. So we did that, we did that, we did that, did that. Wow, did we implement all of our necessary functions? Wow, cool. Dare we try to compile? Alright, got a couple errors. So line 82, cell X undeclared. Because we declared inside of our loop here. No, we don't. Really? Where the hell do we declare? It's inside our for loop right here. That's what the problem is. So we want our line slope between in this case it's going to be our cell span, so it's cell Y plus 2. We can actually do cell Y plus 1 plus plus 0.5, which is, yeah. That'll help spell out exactly what we're doing. So cell Y plus 1 is our loop end condition, and then we're adding, we want the 0.5 to get the right edge of that. You just see we had a couple other errors here. So x1 is an undeclared identifier on line 90. applying. Oh, this is old. We no longer need this. I was incorrect before when I said that this was something we still needed. This is part of our old algorithm. We're applying visibility to our map right here when we mark stuff visible. So then it's giving us on line 98 saying not equals is illegal for a struct. And that's true, so we want this to be a pointer, not a... And because that's a pointer, this fizz is a pointer also, we need to use our pointer access function, or access operator. So game object position return to pointer. Pointer can definitely be compared to null. Let's see. And then similarly on 100 we're using our wait a minute. This needs to be a pointer as well. Okay, and I think that's going to let us build. So we built. So I guess we can let her rip. Now remember, this is only for one sector, so it's not going to be. If it doesn't crash immediately, it's still not going to be what our end goal is. And apparently right now, everything is invisible. So that's not at all what we want. So I'm definitely going to throw this into a debugger so I can step through it because I want to make sure that everything is behaving in the way that we expect it to. I'm rusty at this stuff still, and I would be surprised if there wasn't at least, well, we know that there's at least one bug lurking, but I'd be very surprised if there wasn't at least several bugs lurking in our code. So I am... Let's close that up. I'm going to launch. My Visual Studio so that I can attach to my program. So I'm going to open let me make this visible to everyone. Here we go. So I'm going to set some breakpoints here. But I think I have a phone call. So please bear with me. I will be back in a few minutes. I need to take a call, but I will be back, and then we'll be stepping through our FOV calcs to see. Okay, I'm back. I apologize, that took longer than I thought, but alright. So I'm throwing a couple breakpoints into our code at some interesting locations, and then I'm going to run it and then attach. So let's do that. minute, and debug attach. Okay, so the breakpoint won't be hit. You know, did we? Let's. Why won't our breakpoints be hit? Did we screw up our call to this? Source code is different from the original version. Okay. Let's halt that. Build. Okay. Okay. Let's touch one more time. Alright, it says ready. I am running. Are we just not even calling this anymore? What's going on? Can move. Let's put a breakpoint into. Oh, you know what? No. So our calculation, I wonder if I need to move to get it to trigger. Because if it recalculated wrong, I need to trip another calculation. So let me move. There we go. Okay, so now we've moved the player and we can go through our calculation. I don't need this breakpoint. Let's keep going. It's my resume. Continue. Okay. Continue again. Alright, so now we're in our so we set our previous blocking to false, and now we're going to start looping through each cell in the span, and we immediately fall out of that loop because I miscalculated the cell X and cell Y. So our X right now is we're at 57.2, and I'm not taking into account. I'm assuming that these loops assume that the player is at position 0, 0. So I need to adjust the calculations based on that. Aha! Where's my... Okay, back here. Let's kill the game window. Alright, and so the problem here is that we're not changing cell X and cell Y based on where X and Y are. So we want our offset. So this cell Y is going to be Y plus 1. we start at y plus 1, and then we want it while cell y is less than our FOV distance plus y. Or let's be consistent. We'll make it y plus our FOV distance. And similar with our x, we say for is going to be our x plus 0, and then x plus cell y plus 1. That way we can do proper distance calculations and all of that fun stuff. Now we're going to run into an issue. We're going to run into an issue immediately if our y is out of our map range. So we need to make sure if cell y is greater than cell y is greater than we need to check and see if these coordinates are in our map. So, we need to see if y falls within this is where we need to do some sort of mapping, where we map our cell, which is defined within a single sector, into transform it to a cell within our map. Because this is in map coordinates. Because we've got competing coordinate systems here. You've got your sector coordinates here, which assume an origin on the lower left with x growing as you move rightwards and y growing as you move up, and that is the opposite coordinate system as our map, which assumes that the 0, 0 coordinate pertains to the top left, and you've still got x increasing as you move rightwards, but you've got y increasing as you move downwards now. So now would be a good time to figure out that translation. Because otherwise, this is going to be all off. So anytime when we compare x and y, it's this cell x and y that needs to be transformed. So what we're going to do is inside this inner loop, the very first thing we need to do is translate cell x and cell y to map coordinates. Well, then the problem is the line slope is wrong. So we need the concept of sector cell coordinates and map cell coordinates. And then we need to test is a cell within the map. But my coordinate systems, I'm getting all confused now. I think I need to take a break and think about this more on paper, and then come back and finish out the implementation. Because I've got a hard stop at 4:30 anyway, and that's less than 10 minutes away, so I'm not going to solve this problem in the next 10 minutes. That I know. So I think I'm going to put a stake in it for now. And, oh, you know what? My task list is not showing up. Yeah, Windows rebooted on me, and totally... So the task list has been blank the whole time. I'll fix that for next stream as well. I think that said, we did move a good ways down that road of implementing our shadow casting algorithm, and hopefully next stream we'll be able to finish that up, figure out the conflicting coordinate systems, and then get it mapped to all 8 sectors. And be able to see those results in the game. So, thank you for watching today. If you'd like to be notified next time I go live, which will probably be tomorrow evening, be sure to hit that follow button and you can get notifications for the next time I go live. In the meantime, if you want to catch up on past episodes, the archives are on YouTube. Any questions or comments you have, you can hit me up on Twitter at PDCodes. And if you want to follow along at home, you can grab the source code. I'll be committing today's changes in the next few minutes, but the source code is available on GitHub at the link over here to my right. So thank you for watching, and I'll catch you next time.